Hi, I'm Tal. In this video, I'll give an overview of our paper, DDLP, Unsupervised Object-centric Video Prediction with Deep Dynamic Latent Particles. You are more than welcome to visit the project site, which includes videos and link to the open source code repository, which also includes pre-trained models. In this work, we aim to utilize the deep latent particles representation to model object dynamics in videos. So let me tell you why this is challenging and how we solve it. We begin with a brief introduction of deep latent particles, DLP. The main idea of DLP is a new variation on autoencoder, VAE, where the latent space is not just a vector, but a set of particles. Intuitively, particles represent entities in the scene in a low-dimensional space that will be later used in downstream tasks. So, what is a latent particle? In this work, we extended the definition of a particle from the original DLP with more attributes in what we call DLP v2. DLP v2 provides a disentangled latent space structured as a set of foreground particles where we have the position of the particle as coordinates in Euclidean pixel space, a scale attribute containing the dimensions of the bounding box around the particle, a depth attribute used to signify which particle is in front of the other in case there is an overlap, a transparency attribute, and latent features that encode the visual appearance of the region surrounding the particles, where m is the dimension of the learned visual features. The dimension of each particle is 6 plus m. Moreover, we assign a single abstract particle for the background that is always located in the center of the image and described only by latent background visual features. Every attribute is learned with respect to the optimization objective, the elbow, which is decomposed to the reconstruction error and a KL divergence term. The architecture design of DLP v2 follows the original design of DLP, where the encoder is modified to account for the new attributes. We make better utilization of the learned prior by using its patch-based detection as anchor points for potential particles, which helps with detecting small objects. We utilize the spatial softmax variance to filter detections. Note that in order to learn the particle's explicit attributes in a differentiable manner, like scale and position, we make use of spatial transformer network or STN. We compare DLP v2 to the original DLP on the traffic and object 3D datasets in the single image setting. As shown here, DLP v2 generates particles that exhibit stronger center locking on objects. To model dynamics, it is important to have center lock particles, otherwise the dynamic signal from the latent representation becomes noisy. We present DDLP, Deep Dynamics Latent Particles. In this work, we aim to answer the following questions. How DLP v2 can be used to predict and generate videos? Is the particle representation good for long-term complex multi-object dynamics prediction? And finally, can latent modifications answer what-if questions? The general architecture of DDLP is illustrated as follows. First, for each frame we extract its latent particles. In order to account for alignment between frames, we track the particles over time using an iterative encoding scheme. To model the latent dynamics, we design PINT, Particle Interaction Transformer, which serves as a stochastic prior for the posterior particles. The particle alignment problem. Without any constraint, there is no guarantee that sets of unordered particles will be aligned between frames. To solve this, we draw inspiration from the tracking literature and use an iterative encoding scheme where the particles from the previous frame serve as anchors for the consecutive frame, and the offset from them is learned. In addition, for a more accurate tracking, we use cross-correlation between patches or glimpses to get a better lock on the object displacements in a consecutive frame. Note that our underlying assumption is that the displacement or delta between frames is small. This assumption would not hold in case objects can vanish and reappear in different locations. We can see that the particles are tracked correctly across time. Let us continue and discuss the dynamics modeling. Similarly to other VAE-based video prediction models, the dynamics are modeled as a stochastic prior. The transformer outputs the prior distribution parameters for the particles of the consecutive frame. We modify the causal attention operation to allow particles to attend to each other in the same time step and across time. K is the number of particles. Finally, we replace the absolute positional embedding with relative positional embedding, both for the time and for the particle identity. The relative positional bias is built as follows. The positional bias is added directly to the attention matrix. Training of DDLP is performed end-to-end. All components are jointly trained. We also use burn-in frames to drive the dynamics. The intuition is that in order to infer dynamics such as acceleration or velocity, it is not enough to observe a single frame. We use tau equals 4, that is 4 burn-in frames in all our experiments. There are several families of methods related to ours. Note that all methods that use transformers are typically not trained end-to-end. Our main baselines are the state-of-the-art patch-based method GSWM and a slot-based method slotformer. Let's see some results. Here, note the deformation in the long-term predictions of GSWM. Here, note the vanishing cars in GSWM's prediction. We also provide quantitative results where we measure the L-pips of the generated frame with respect to the ground truth frame. For the Bose dataset, we also calculate MET10, the mean Euclidean error between ground truth and predicted ball location in the first 10 predicted frames. More ablations and metrics can be found in the paper. We have implemented a graphical user interface to interact with the particles, where we modify scenes and unroll the effect of the intervention. We can also do interpolation in the latent space, as this is a VAE, and we can draw a linear line between the modifications in the latent space and animate the interpolated trajectory. DDLP provides us with an interpretable latent representation. We can directly modify scenes in the latent space by changing objects' learned attributes. Equipped with a pre-trained DDLP on Object 3D, we take an initial sequence of frames, encode them to latent particles, and manually locate and modify specific particles corresponding to objects of interest according to a specific scenario. For example, what if the green ball here moved to the left? Then, we unroll the latent sequence with the dynamics module and the code to produce a video of the consequence of our interventions. We can see that Pint generalizes well to our interventions, allowing us to ask what-if questions. We also introduce a diffused DDLP, an approach for generating videos from scratch. We train a diffusion model's DDPM to approximate the distribution of the latent particle sequence of length tau. Equipped with a trained DDPM, we sample sequences of tau particles and use them as input to the pre-trained DDLP dynamics model Pint to unroll the sequence to horizon t, where t is greater than tau. Finally, we generate a video by decoding the sequence of generated particles back to pixel space with DDLP's pre-trained image decoder. Our denoiser is based on Pint. Due to the unique structure of DDLP's latent space, a denoiser architecture that considers the evolution of set of particles over time is required. To that end, in diffused DDLP, we repurpose Pint to perform denoising instead of predicting the next state of the particles. In our initial experiments, both the 1D and 2D unit introduced unsatisfying visual artifacts. Here we can see generation results of the first tau frames represented as latent particles by the DDPM of diffused DDLP, where here they are decoded to pixel space with DDLP's image decoder for visualization purposes. And here we can see generated videos. In conclusion, we extended DLP to video and particle dynamics modeling. We demonstrated state-of-the-art result in object-centric video prediction, and we also demonstrated video latent manipulation and asked what-if questions. Finally, we introduced video generation by diffusion over particles. We see great promise in modeling dynamics with the particles representation as a tool to understand the consequence of interventions, potentially in reinforcement learning where actions are also involved in the physical dynamics. Thank you for watching, and please visit our project sites for more information, code, and pre-trained models. Thank you.